thanks. So I'm Sam Brilleman. I'm a PhD student at Monash University in Melbourne in Australia. And this talk's work that I've done alongside my PhD supervisors, so Michael Crowder, who's based in the UK, Margarita Marino-Bedenker and Rory Wolf, who are based in Melbourne also, as well as a collaborator, Jackie Virosnovic, who's on the East Coast here in the US. So just briefly, an outline of the talk, I'll give a bit of context and background, and then I'll describe more the formulation of a shared parameter joint model, and more explicitly describe some of the association structures. I'll then describe the software implementation I've been working on for these models, and provide a few slides showing the functionality using an example application. So some context. We're going to be in the setting of biostatistics, and suppose we observe repeated measurements of some clinical biomarker on a group of patients. So these might be clinical trial patients, or perhaps there'll be some observational cohorts, such as if we have some registry-based data set. So here, for example, in the picture, we've got some patients with liver disease, say, and we might measure serum bilirubin and serum albumin on these liver disease patients. And rather than doing this on one occasion, we do it repeatedly over time during the course of some follow-up. But then suppose also that we want to measure the time from some defined baseline, and this might be something like diagnosis of the disease, until some meaningful clinical endpoint, event endpoint, such as, say, death. So we might think about how we can visualize this type of data. So here I've got plots of the observed biomarker measurements over time. So here I've got 4 liver disease patients, each one shown in a separate column. And in the top row we have observed biomarker trajectories for log serum bilirubin, and in the bottom row we have serum albumin. And so we can see there's between patient variation in these trajectories, some going up, some going down, some flat. And we also want to somehow represent the event outcome information here. So I've just used solid lines for those individuals who didn't die by the end of their follow-up period, and dashed or dotted lines for those individuals who had died by the end of the follow-up. And so we're going to talk about the joint modelling of these two data types. And so what do I mean by that? Well, under the joint modelling framework, we're going to treat both the longitudinal biomarker and the event data as outcomes, and we're going to model each of those outcomes using a distinct regression submodel. So for the longitudinal biomarkers, we're going to use a mixed effects model, or multi-level model, or hierarchical model, whatever terminology you prefer to use. And in the case of multiple biomarkers, so in the previous example we had serum bilirubin and serum albumin. So there we have 2 biomarkers, and would be thinking about fitting a multivariate mixed effects model. And I'll describe the parameterization of that in later slides. And then for the event outcome, we have a proportional hazards regression model for the time to event outcome, and we're going to link these regression submodels through shared individual specific parameters or patient-specific random effects. And an important thing to realise here is that although we have these so-called distinct regression submodels, we're going to estimate them simultaneously under one joint likelihood framework. So why might we use these approaches? So there's a few different reasons, but some of the more obvious ones are we want to understand something about the relationship between the longitudinal outcome, or some function of that longitudinal outcome, and the risk of the event. So this is epidemiological type questions related to the potential for etiological associations or causal associations. But there might be other reasons. So one area in which these joint models have been shown to be useful is for dynamic clinical risk prediction. So we could fit this joint model, and we could use some individuals' biomarker measurements to predict their risk of the event. And then as they come into the clinic at some later time and have new biomarker measurements observed, we can use those new measurements to kind of dynamically update or time update their estimates of the event risk, their predictions of the event risk. So, and it's probably worth noting here that although all the developments in this area have been in the biostatistical literature. There's potentially unrealised potential for these models to be used in other disciplines, I guess. So the formulation of the shared parameter joint model looks something like this. So as I mentioned, we've got these two submodels, and at the top we have the longitudinal submodel. So here Y is going to be some observed measurements on our mth biomarker, and it's going to be for individual I at some time point J. And what we're going to do is model that in continuous time, where we assume Y follows some distribution in the exponential family with some mean mu, and we're going to link mu to eta through some link function g. So here we have a generalized linear mixed model, and we've indexed this link function g with a subscript m to show that the family and the link function that we use can differ across the different biomarkers if we wish for that to be the case. So then, as part of our linear predictor, we have some observed covariates or data, so vectors here x and z, and then we have some population level parameters beta and some patient-specific parameters b. And what we can do is collect the patient-specific parameters across the different biomarker submodels and collect them into this single vector, so this combined vector of patient-specific parameters bi, and we assume that follows some shared multivariate normal distribution with unstructured variance covariance matrix here sigma. So what sigma does is it allows us to capture some of the dependence between the different clinical biomarkers that we might observe. So that's our longitudinal submodel. We then have our event submodel. So here, proportional hazards regression model. So HIT here is the hazard of the event for individual I at time t, and it's equal to some baseline hazard H0 t. And then inside the linear predictor here, we have some covariate data again. So this vector W and its associated population level parameters gamma. So gamma here is going to be log hazard ratios. And then we have this term on the right, which we refer to as the association structure. So it captures the association between the longitudinal and the event processes. So we can parameterize that in different ways, and the example I've got here we refer to as a current value association structure, because what we've done here is assumed an association between the hazard of the event, or the log hazard of the event, and the current expected value of each of the biomarkers. So all of these things are calculated at time t. So a couple of things to note here about some of the benefits of this joint modelling approach compared to alternatives. So one alternative would just be to use the observed biomarker data and use that as a time-varying covariate in some models, such as a time-dependent Cox model. But if we were to do that, we'd be using Y, and Y is subject to both measurement error, and it's also measured in discrete time. Whereas by using mu here and mu entering into the event submodel, we have a quantity that's free of the measurement error, and it's also modelled in continuous time, so we can evaluate mu for any value of t. So what this means is that our what we call association parameters, so these parameters alpha, are going to be less biased than if we had used this alternative approach where we just use the observed biomarker data as a covariate. Okay, so that's one formulation based on this current value association structure, but we can generalize that. So a more general form for the event submodel looks something like this, where we now have this summation over Q, and we have some functions that are currently undefined, F, which is subscripted with M and Q. And so what this formulation says is we've got some association between the log hazard of the event and any function of the parameters from the longitudinal submodel. So we can think of specific cases, and the one on the previous slide was one of those specific cases. But some of the other more common ones might be these. So eta, where we have the linear predictor evaluated at time t. Alternatively, we might think that the hazard of the event at time t is related to the rate of change in the biomarker at time t. Or this third one, the hazard of the event is related to the integral, either under the linear predictor or the biomarker trajectory between baseline and time t. So this might make sense if we had say, dose concentration as our biomarker, and we wanted to calculate the cumulative effects. And this last one, we might assume that the hazard of the event at time t is related to some earlier value of the biomarker, so some lagged value, where t minus u is some time for a lag time u. So what's been done in the way of software for these joint models? So there's been a whole bunch of methods development, but not all of it gets translated into user-friendly software. So there's pretty well-established software for one longitudinal outcome, so there's packages in Stata, R, and SAS now, but it's only been in the last, say, year or so that anything's been released that can handle multiple longitudinal outcomes or multiple biomarkers. And so there's a few packages in R that have come out recently, and the one I'm going to highlight in this talk is RStanArm, obviously. So as of the most recent version of RStanArm, so 2.17, that's just been released on CRAN a few weeks ago, there's joint modelling functionality included. So most of you are probably aware of what RStanArm is, but for those of you that aren't, RStanArm is an R package built on top of the R interface for Stan, so it allows the user to fit models, or some regression models, using standard R formula syntax and data frames, rather than having to write any Stan code themselves or pass the data. So in terms of joint modelling, in this most recent version of RStanArm, we have a bunch of features, so multiple longitudinal outcomes, multi-level clustering, so patients clustered within clinics, for example, a variety of families, link functions, association structures, baseline hazards, and so on. So I'll just spend the last few minutes talking through an example application that will just show some of the functionality or a few of the functions that we can use in the RStanArm package. So I'm going to use a widely known data set in the biostats literature. So this is freely available, the PBC data. So it contains 312 liver disease patients who participated in a trial a number of years ago. And we're not going to be concerned with looking at treatment effects here. Instead, we're just going to look at the associations between bilirubin and albumin, so two biomarkers that were measured on those patients over time. And we're going to look at their association with mortality. So we'll model each of the biomarkers using just a linear mixed model to keep things simple, with a random intercept and a random linear slope. And then the event submodel will just have gender as a baseline covariate, and we'll assume this current value association structure that I showed on the earlier slides. So the code for fitting the model using RStanArm looks something like this. So we have the stan_jm function, and we have to pass in arguments for the formulas for each of the submodels. So here, because we have two biomarkers, the formula for the longitudinal submodel takes the form of a list of formulas, and we have a formula for the event submodel. We then have arguments for the data frames for each of those submodels, and we have to tell RStanArm or tell stan_jm what the name of the time variable is in the longitudinal submodel. We then optionally have these last two arguments, so for this we're using the defaults, so we could have left them out, but we specify the association structure here and the baseline hazard, just to be explicit. So then the R package goes away and fits the model using Stan, and we get back the fitted model object, and we've got a bunch of generic methods we can call on that fitted model object. So here the print method gives us some output that shows us summary descriptives of the model at the top. Okay, and then some estimated parameters in each of the blocks below. So we can see for the population level parameters here, we can interpret, for example, for the event submodel, that a 1 unit increase in log serum bilirubin is associated with a 2.1-fold increase in the hazard of death. And at the bottom of this output, we get some information about the patient-specific random effect structure. We then get some more detailed summary output from the summary method. So at the top here, we have more information like runtime for the model, posterior sample size, and so on. And we can use this shortcut pars equals ASOP to get just information about the association parameters. I'll just quickly finish with one example showing how we can get in-sample predictions. So here we're just going to predict for two individuals that we used in the estimation of the model, and we're going to predict longitudinal trajectories and also survival functions conditional on their last known survival time and projecting forward. So we can calculate those using these posterior underscore trajectory and posterior underscore serve fit functions, and then generate some plots. So here we can see on the left one individual and on the right another, the one on the left having better survival, so the survival function shown down the bottom here, where the dashed line is their last known survival time. Last known survival time. And we can see the individual on the left has better survival probabilities given that their biomarker measurements show better values. Okay. So just some acknowledgements, which I'll leave in the interest of time. And I'll just finish on a shameless plug for the joint Australian Stats Conference and International Society for Clinical Biostatistics, which is happening in Melbourne later this year. So if you wanted a holiday down the southern hemisphere, then maybe this would be your excuse. So, cheers.
Any questions?
Two questions. We're also looking at joint models in the work that I mentioned before, and a couple of things have come up. One of which is that the proportional hazards assumption isn't always such a good thing. So we're wondering if things other than proportional hazards work in RSTAN arm easily. And the other question is traditional joint modeling packages do not allow the. I mean, you've got the time to event model, and you've got the model for the biomarkers, basically the continuous biomarkers. And in a lot of the things we're looking at, it makes sense for the continuous biomarkers to continue after the event. So obviously the event can be death. So the question is this flexible enough so that the continuous part of the continuous biomarkers models will continue after the event has occurred?
Yeah, okay, so on the first one, so there has been some work previously looking at accelerated failure time models rather than proportional hazards. So I know Demetrios Rizopoulos discusses some of that, especially for his earlier package, JN, or at least in his book. So it hasn't really taken off. I guess partly maybe some of the limitations around parameterizations for the accelerated failure time models as well. Although my supervisor's Michael Crowder in the UK, and he's also been working on more flexible specifications of accelerated failure time. So maybe in the future there'll be a method for combining, sort of those two things: flexible parametric accelerated failure time models and putting them into the joint modelling framework. But at the moment, so it doesn't have to be proportional hazards, but there hasn't been that much work looking at the alternatives, I guess. Proportional hazards has been the norm. In terms of the other one, so the other was...
Whether the biomarker processes can continue after the event.
Okay. So there's also been some work looking at recurrent events, fitting recurrent events into this kind of framework, whether it be recurrent and a terminating event under the same model, or whether it just be recurrent events alone with the continuous biomarker process. So I guess that's one area. So if the event is a recurrent event, you could cope with it.
Let me mention quickly the sort of event we have in mind. There's an event called in HD Huntington's disease. We know we can get the disease before they get it because its genetic tests are available. But there still is a diagnosis of the disease, a clinical diagnosis that occurs, and that's made by a physician, and it's independent of whether what's known about the genetics of the patient. That diagnosis can be predicted with a lot of other variables, and those variables will continue to occur after diagnosis. So, in a sense, we have that's a particular example, but I'm sure there are a lot of cases where an event, unlike death or something, the event occurs only once, but but it's only part of the
Yeah,
whole
okay.
process.
So there has been some work, I think, not a lot, but looking at multi-state models in this sort of, under this joint modelling framework as well. I don't know much about it, and none of it's implemented in StanCon. But yeah, I guess we could talk about maybe that later on, what the options are.
Thank you. Interesting one.
Thank you very much, Sam. We'll break.